Okay, so you should be seeing now my, my first slide, the title, Indeterminism in Physics and Intuitionistic Mathematics. So indeed, it's an unusual topic for physicists, actually also for mathematicians. So essentially, maybe one thing, so you said already that at the University of Geneva, I'm actually now also in this Schaffhausen Institute of Technology, which has a branch in Geneva, and I'm also actually half-time full professor there. So the talk is structured with some motivations at the beginning, which will emphasize that there are several actually mathematical languages. We are all used to what I will call classical mathematics, but it's not the only one. Also in the motivation, I will use a lot of classical chaos as an example. Maybe if you just want to remember one catchy sentence, it's that one: real numbers are not really real. And then I'll come to intuitionistic mathematics, which will actually be half of the talk, more or less. And at the end, something about the relativity of indeterminacy. Okay, so motivations. So far, I guess everybody will agree, physicists produce models of reality, and these models should be faithful. In particular, that means that the empirical predictions should be correct. But one important aspect in my view is that this is not sufficient. Indeed, there is a second requirement for a good physical model, namely that this model should allow us, humans, to tell stories about how nature does it. So now what is a story? I'm not going to tell you that in philosophical language, but maybe just some example that you see here, you know, the tides, gravity, Brownian motion, and all these kind of things. We can tell stories about all these processes. Okay, now I don't see all of you because of this strange situation with this annoying virus, but I suspect, I'm pretty sure that the vast majority of you are high energy physicists. So you have been nourished with general relativity, and the normal picture that you have in mind is this one, the block universe. Actually, let me use that pointer. Yeah. You know, in this block universe, you have the past, the future. There is this infinitely narrow slice, which is the now, which is what we experience now. And in this picture, everything is fixed since ever and forever. And for instance, Einstein put it in the following way: people like us who believe in physics know that the distinction between past, present, and future is only a stubbornly persistent illusion. Okay, but also Wolfgang said in the introduction, I'm not coming from this world, from relativity. Let's say I'm more on the quantum physics side. And so in quantum physics, let's say the kind of picture we have in mind is more things like that. You know, have photons, for instance, binging on a beam splitter, you know, let's say 50-50. And then they get detected either by this red detector, which I label as a 0, or the blue one, which is a 1. And then we get a string of bits out of that device. So this is a sketch of a quantum random number generator. But very important is that here, with this kind of view in mind, we are used to, with a quantum physicist, we are used to that. New information gets created as time passes. And there is clearly a serious tension between these two views. Of course, now I could mention quantum gravity and so on. So I don't claim that I have a solution for quantum gravity, but this is really my background. And let me tell you a bit more about this background. So first about this quantum indeterminacy or quantum chance, to cite the book that Wolfgang mentioned in the introduction. You can put a distance between two of these quantum random number generator. And let's say that you have the possibility to rotate maybe some polarization beam splitter or change the phase here. So you have some you have different possible measurements that you can perform, both on Alice's side, let's say the left side, and on the right-hand side. And you have, of course, outcomes coming here. Really try to put that. Yeah. Okay, now let's make some assumptions. And the first one is to assume no instantaneous communication at a distance. Of course, many people just say no faster than light, but actually it's even sufficient to say that there is no instantaneous, even if things would go faster than the speed of light, but still at a finite speed. That would be excluded by this assumption. And the second assumption is about no conspiracy. Or maybe people know that I know superdeterminism. And what I need is really that there exist independent variables, in particular that these inputs here on both sides, Alice and Bob, are independent of any hypothetical variables here in the source, whether it influences a quantum or a classical variable. Okay, so these are two assumptions, very, very natural. And then there's an experimental fact. Okay, I write it in this way, but this just means a violation of some Bell inequality. And then there's a theorem, just a mathematical theorem, which says that these outcomes, A and B on Alice and Bob's side respectively, these outcomes are truly random. And you can learn more in this book or in this review of modern physics paper here. You can also go to the original paper here, or you can also make all that quantitative. So how much randomness is there here? So this randomness in bits here, depending on the violation of some inequality, in this case, a CHSH inequality. Okay, so this exists. And as you already see here, this can be really made very small. And actually, last year, the spin-off company of my university group, IDQ here, managed to put all that into a little chip, millimeter size, and very important, very low power consumption. So at the end, you can put this chip into a smartphone. Okay, here you can even read the name of the company. And once you have this chip in your smartphone, you really have a smartphone that produces quantum randomness. And with this quantum randomness, you can have it for all kind of applications, cryptography, mobile banking, and things like that. Okay, it's available today only in Korea and Vietnam. And why is it only in Asia? That's a very good question, but outside the scope of my presentation, probably also outside of physics. Okay, so let's continue with the motivation. So we want to be able to allow humans to tell stories that includes this new information that gets created, for instance, in a quantum random number generator, or more generally, gets created by nature. And let me immediately tell you the main messages. So the first one is the following: whether Newtonian classical mechanics is deterministic or not is not a scientific question. It really depends on the physical significance one associates with mathematical real numbers. The second message, of course, I will elaborate on all that. The mathematical language we use when speaking physics has a huge influence on the world view that physics presents to us. I mean, I'm sure that we all speak more than one language. Of course, all speak and understand English. Probably many of us speak also some French or German or Russian or Chinese or whatever. And we all know that depending the language we are using to convey some concept and ideas, there are concepts and ideas that are easier to express in one language than another. And the mathematical language is not different. I mean, some mathematical language are easier to express some views, and some other language are easier to express some other views. Of course, we'll come back to that. And at the end, so we face a choice, since there are more than one mathematical language. We face a choice. Either our stories present events as the consequence of long past initial conditions, as in the block universe, or else we understand the present as the result of indeterminate reality, and the future is open, which is closer to the view, or the quantum view, let's say. So let me now come to intuitionistic mathematics. But first question, of course, is why do I talk about intuitionistic mathematics? I'm not a mathematician. There are many people who understand intuitionistic mathematics much better than I do. I'm just a physicist. But as I already said, to do physics, we need, of course, concepts, appropriate mathematical tools, concepts. But then the question comes, which mathematics? This I have already said and emphasized. This language, this mathematical language, is going to condition the ideas we express. So Brouwer, he was a Dutch mathematician a century ago, and he's the father of intuitionism. And Brouwer himself introduced into his mathematics the concept of an ideal mathematician. Sometimes he called it the creating subject, who continuously produce new information by solving mathematical conjectures. So Brouwer was a very special character, actually a complicated character. He had fights with many of his fellows at the time, particularly, as we shall see, with Hilbert. And also his views were very subjectivist. He was almost a solipsist. And that's clearly not the way most physicists, and certainly not the way I am. I'm certainly not a solipsist and not even a subjectivist. So I will present actually intuitionism without any ideal mathematician, and I will motivate intuitionism by the physical concept of indeterminism. So it is likely that Brouwer, passed away, of course, not many decades ago, would not have liked my presentation, because actually I'm just a physicist and possibly naive realist. So my claim, or my main claim even, is that intuitionistic mathematics is the natural mathematical tool to describe indeterminism in physics, similarly to derivative, which is a natural mathematical tool to describe velocity. Okay, so let me now give you a first encounter with intuitionism. Let me start with the claiming that numbers are there to compute. Probably most people would agree on that. But then, how is it that most of the so-called real numbers are not computable? Let me define some integers. So here it's real number, we'll come back to that. But let's start with something very simple, integers. And actually I'm going to talk about bits, 0 and 1. Very simple concept, seemingly. And let me define first the following bit, n1. And I define it as follows. So n1 equals 0 if every integer between 4 and 10 to the 4 is the sum of 2 primes, and n1 equal 1 otherwise. So maybe you don't know the answer, so you don't know the value of n1, but there's no doubt that you could just, everybody could just jump on his computer in a matter of a few minutes, find the value of n1, and find actually that n1 is equal to 0. But even without doing that, you know that n1 is either equal to 0 or equal to 1, no doubt about that. Let's now consider another bit, n2. Similarly defined, n2 equals 0 if every integer between 4 and a huge number is the sum of 2 primes, n2 equal 1 otherwise. Now here, well, we still don't know the value of n2, and it's not good enough just to jump on a computer because this number is huge and you will not find the answer in your lifetime. Or if you find it, you can always make this number a bit larger. Okay, but still there is a clear procedure that we all understand that in a finite time, a very long time, but in a finite time with some, okay, there's an algorithm, a finite algorithm that tells you for sure that after a finite time you get an answer. So n2 has a value. Either n2 is equal to 0 or n2 is equal to 1, irrespectively of us knowing this value. Now comes the third bit, n3. equal to 0 if every even integer is larger than 4, up to infinity, unlimited, and n3 equal 1 otherwise. So this is actually a mathematical conjecture, an old conjecture called the Goldbach conjecture. And no one knows the answer. No one knows the value of n3. And more importantly, there is no known algorithm which allows one to compute n3 in a finite time. So even a very long but finite time, we just don't have an algorithm to compute this number n3. Now, yeah, I guess nevertheless, every student and probably everyone here in this Zoom meeting knows that, okay, for a student not to fail an exam, he has to claim that n3 has a determined value, either 0 or 1. But that's the crux. If the exam is in intuitionistic mathematics and not in classical mathematics, then the student should answer that the value of n3 is indeterminate and that the law of the excluded middle is not valid. So for instance, the proposition n3 equals 0 is neither true nor false, but is indeterminate. It's really intrinsically indeterminate. It's not a matter of knowledge. It's a matter that there is no value for this bit here. So this is already very strange. I'll emphasize, I come back to that and explain that and my intuition behind that. But actually, it's not even the end, because there's something else which is very central in intuitionistic mathematics, namely that the value of n3 may evolve over time. Because indeed, maybe tomorrow, in 10 years, someone will find an algorithm to solve Goldbach conjecture. And then the value of n3, according to Brouwer, will change, will move from indeterminate to determinate. So very different flavor here compared to the mathematics, the classical mathematics we have all been nourished with. So let's just tell you a bit more about this intuitionistic standpoint. So Karl Posse, a philosopher but who knows a lot about intuitionistic mathematics, wrote the following: we humans have finite memories, finite attention spans, and finite lives. So we can fully grasp only finitely many finite-sized pieces of a compound thing. There is no infinite helicopter allowing us to survey the whole terrain and to tell how things will look at the end of time. So somehow you already get this first idea that if we could really see all the future and survey the whole terrain and go to the end of time, then everything would be determined and we would end up with classical mathematics. But we are within time, and so today not everything is determined. Another mathematician, Gerhard Bishop, who is one of the fathers of constructivist mathematics, wrote the following: the classicist wishes to describe God's mathematics, the constructivist to describe the mathematics of finite being, man's mathematics for short. Constructive mathematics does not postulate a pre-existing universe with objects lying around, waiting to be collected and grouped into sets like shells on a beach. And Brouwer himself wrote things like that. Nature simply has not yet fully determined all objects. And this can be somewhat compared, at least with some flavor, of the uncertainty principle that we know from quantum mechanics, which, by the way, should be called the indeterminacy principle of quantum mechanics. So that's the essence of intuitionism. Now maybe some of you get worried. I mean, that's a very strange form of mathematics. How could there be things, including mathematical objects, that are not fully determined? So maybe to calm this kind of worries, let me state that with intuitionistic mathematics, you can compute and prove theorems. Maybe not always the same theorems as in classical mathematics. I will come back to that and give you some examples of theorems that are a bit different or that are new, so on. Or maybe also sometimes just the proof has to be adapted. But for sure, everything one can do on a classical computer can also be done with intuitionistic mathematics. Hence, all of physics can be done using this different kind of intuitionistic mathematics. Actually, now I just remember that I was supposed to stop my video. Is there still somewhere here? I cannot hear anyone. I cannot see anyone, as usual. Can maybe someone just say something to make sure that I'm still online?
Yeah.
Yes.
We can hear.
We are here. We are all here.
Okay, excellent. Thank you. Let me just stop my video, which I guess you don't need anyway. And okay, very good. So let's continue. Now I have to come back here. Oh. Okay, so one very important and very timely kind of physics is climate physics. And actually the people doing climate physics, they use truncated numbers. Indeed, what can they do? They go into their huge computers, they simulate the climate in the next decades. They have only access to finite information anyway, and their computers are finite anyway also. And because this is a stochastic process, the climate, at some point when they run their simulation, they need new numbers, so additional information that they cannot measure. So what they do is to add stochastic reminders. You can, for instance, read that from this paper by Tim Palmer, a British climate physicist. So actually, there are physicists already today that at least in practice use, without really knowing about it, intuitionistic mathematics concepts. Okay, so let me now turn to my personal motivation. I was kind of rediscovering intuitionistic mathematics before learning that this already exists. And I started with chaotic classical dynamical systems, which I usually consider it as deterministic. So now why classical dynamics and not relativity or quantum? Well, classical physics has one advantage, namely that we understand it very well. We have all good intuition about classical physics. Moreover, we understand that there are limitations to this kind of physics. And we know the boundary conditions or the domain of validity. We know that things become small compared to Planck's constant. Then we have to turn into a quantum. And if things move fast compared to the velocity of light, we have to go to relativity. So it's a well-known and understood physics. Okay, so comes the question, is really classical dynamics and classical chaos deterministic? Or is it actually the consequence of the language we are using, namely classical mathematics? So assuming this God's eye view, or the view of the end of time. So to cite another philosopher, Yuval Dolev, he wrote that the tense and passage are never were and probably cannot be part of physics and its language. So indeed, with classical mathematics, it's essentially impossible to really talk about the passage of time. Okay, let's take an example of a chaotic system. Let's take something very simple. So the state space is just a number between 0 and 1 in the unit interval. And the time step is described as follows. It's essentially the Baker map. So you stretch that, double it, and then you fold it back. So mathematically, it's this function. And this function, if you write the x, the variable in the state space in binary format, so 0 dot and then a series of bits, then these time steps are described the following. You just drop out the first bit, the second bit becomes the first one, the third bit becomes the second one, the fourth bit becomes the third one, and so on. Just shift. And then indeed, it's pretty obvious that under this map, whether x lies on the left half or on the right half of this unit interval after n steps depends on the nth bit of the initial condition. And now comes the, okay, maybe then you could say that if it's this is the probability of rain, and okay, so if it is below 1/2, it is a good chance to be sunny. If it's larger, it's a good chance to be rainy. And then the question comes, is the millionth or the billionth bit physically real? The question is not whether we can measure this far down the series bit. We cannot measure it. But is it physical? Does it correspond to something real or something physical? And clearly, if you say, no, it doesn't correspond to anything physical, then in the course of time, it has to get physical, because at some point, the weather will indeed be either sunny or rainy. So let's consider these real numbers, and specifically typical real numbers. And it's very strange that actually all real numbers, so the numbers from classical mathematics, the one we know, but all the real numbers one encounters are actually exceptional. They are exceptional because they have a name and they are defined by some algorithm, of course, a finite algorithm, like square root of 2 or pi or a fraction, integer. All these ones are special. Because the bits of a typical real number, the vast majority, have no structure whatever. So the bits of these typical real numbers, they are random, actually. They are as random as quantum measurement outcomes. So somehow you have randomness in classical mathematics, but hidden in the bits or the digits of real numbers. And so one good way of thinking of a typical real number is exactly like that. And you remember, this is a sketch of a possible quantum random number generator. And what comes out here, you may say, is a typical real number. And indeed, since there are only countably many names and algorithms, typical real numbers contain an infinite amount of Shannon information. You have these bits coming out, and it's a never-ending series. So it has an infinite amount of information. And the fact it has this infinite amount of information was nicely illustrated by Emile Borel, who noticed that one real number can code the answers to questions one can formulate in any human language. So you have one number which we could code, of course, it's not a constructive way, but it could code the answers to all questions we could have, let's say binary questions. And so as Gregory Chatin noticed, this way of thinking of a typical real number is not only a possibility, but it's the only good way of thinking of a typical real number. It's really an unlimited string of outcomes of a true random number generator. It doesn't need to be quantum, but it has to be a true quantum random number generator. Okay. So when we say, for instance, that x0 is, let's let x0 be a real number, what we're effectively saying, let x denote an infinite amount of information. Yes, and here is my motivation, but you may buy that one or not, doesn't matter. But the idea here is that finite volume of space implies finite information. So if you have, for instance, this cubic centimeter, or some finite volume, and you have, let's say, a billiard ball in it, this finite volume cannot contain infinitely many bits. So for instance, the position of this billiard ball cannot be a typical real number. Now you may say, okay, that's well known, it's Bekenstein bound. Yes, of course, I agree with that. But I think with Bekenstein bounds, one uses quantum field theory and black holes. And here I'm talking about classical mechanics. But I think in classical mechanics, it also makes sense to assume, here it is an assumption, but just to assume that finite information density also applies to Newtonian mechanics and to special relativity, without black holes. So the consequence is, first, yeah, of course, Descartes named these numbers real because he wanted to contrast them with imaginary numbers, but that doesn't make them really real. So the mathematical real numbers are actually not physically real. Actually, these mathematical real numbers are physically random. And of course, these random numbers cannot be the basis of scientific determinism. So my intuition is the following. So you have in a typical number, you have the first digits which are clearly determined. If you go very, very far down the series, they are fully indeterminate. But in between, you may have a transition, and I'll come back to explaining that, where these numbers are more or less determined. They have some propensity to turn out with some value. Okay, so that's the first message. Whether Newtonian classical mechanics is deterministic or not is not a scientific question. It depends on the physical significance one associates with these real numbers. Okay, and here there's again a citation of some philosopher, but let me go up. So once we agree that there could be some indeterminacy in nature, physical model, sorry? Okay, if there could be some indeterminacy, then a natural reaction would be to say, let's add some supplementary variables. Maybe we are missing something. This is very well known in quantum mechanics, where people were looking for, additional hidden variables. So the general idea could be that, instead of God playing dice when potentialities become actual, we could make a physical model in which God played all dice at the initial time, and God coded all results in the initial condition. And here again, we face this choice. Either the fact that at present certain things happen and other do not is interpreted as revealing retroactively information about long past initial conditions, or else we understand the present as the result of indeterminate reality and the future is open. So if you apply that kind of idea not to quantum mechanics but to classical mechanics, with the idea that there is this finite information density, you could of course say, no, it's not as time passes that additional bits in the series of this initial condition gets determined. Everything was done at the initial time and everything was coded into the initial condition. And in this way, you can now understand that real numbers are the hidden variables of classical mechanics. And interestingly, the fact is that almost all physicists accept real numbers without even noticing that these are supplementary variables, while these same physicists usually reject Bohmian positions. Bohmian positions is a non-local hidden variable model of quantum mechanics, and we reject these Bohmian positions as unnecessary. Okay, so we know that there was a century ago, more or less, this big Einstein-Bohr debate. We also know, at least everyone interested in time knows, that there was a big also encounter about time between Einstein and Bergson, also about a century ago. A bit less known is the fight or the tension there was between David Hilbert, the famous mathematician, Hilbert spaces, the Hilbert problems and all that, and Brouwer, the father of intuitionism. So on Hilbert's side, you have classical mathematics, the mathematics we all know, in which every real number is an individual completed entity. All digits are given at once, and the continuum is a collection of individual points. So these real numbers, they exist somehow outside time in some idealized Platonic world. On the other side, on Brouwer's side, with this intuitionistic mathematics, real numbers are processes that develop in time. The next slide starts presenting that in detail. So digits here are not all given at once, except for computable numbers, where you have a finite algorithm. And the continuum is a viscous collection of processes. Again, I will define a viscous collection in a little time. So here on the intuitionistic mathematics side, time is essential because at any instance, only finite information exists. So now let me present intuitionistic mathematics. So Brouwer himself, he introduced some mathematical object he called a choice sequence, this alpha of n being an integer, where the choices are made by this idealized mathematician, which I already mentioned. Now, let's replace this idealized mathematician by just the assumption that nature has the power to produce true randomness, hence to produce new information. And indeed, if you want to develop a mathematical model of indeterminism in physics, you need the possibility to add new and fresh information as time passes. So let me call that natural random process, NRP, that produces at each time instant one random bit, Rn. Now these random bits at each instant, each time step or instant, this natural random process output this random bit, as I just said, and then we define the elements of this choice sequence, alpha n, as a function, okay, of the previous value of the time step and all the existing information. So all these random bits, but only until time n. And assume this function to be computable so that I get a computable number. So I have a series or a choice sequence of computable numbers. Okay, and then I also make the assumption that there is some convergence. So this alpha n is going to converge. Here's a first example, a very simple one. Let's just assume, I call this number, these choice sequences, totally random number. So here we have just that the alpha n is the previous one, and the nth bit is just the output of my natural random process. So it's really exactly the picture I gave you before. A second example, still a very simple one, computable numbers. So here the alpha n will not depend on all the available information, but at some point it stops. It just takes the k first random bits. And this is now just a finite information. And then it goes on, and what you produce in this way, or at least what you could produce, are these pseudo-random series. And let me just illustrate that with one typical computable number, pi. And we know that there are actually even several algorithms that allow one to compute pi. Here is an example on the bottom here. What is interesting with this specific, okay, now this is still general. Of course, it takes time to run the algorithm, but every bit can be computed in a finite time with this finite information, which is actually written on the bottom here in this algorithm. Now, what is interesting with this specific algorithm here is that although the bits may look random, like in these pseudo-random sequences, they are actually hidden in the algorithm. And for instance, in this algorithm, one can compute the nth bit or the nth hexadecimal of pi without computing the previous ones. You can really directly jump and say, I want to know the bit, the billionth bit of pi. And with this algorithm, you can compute that billionth bit without the necessity to first compute all the previous bits. And that, I think, is a very nice illustration of the fact that the bits of computable number, specifically of pi, don't come one after the other. They are already all there. If they would come one after the other, you could not jump to bit 1 billion without first computing all the previous ones. So let me come now to another example of an intuitionistic number, which is very close to the intuition I already presented. I call them finite information quantities, or FIQs. So here the additional bit is a majority vote over the k last random bits. And in this case, you get some correlations among the bits in the series. So for instance, here you would first have that some bits are fully determined up to the bit number n, because here all the information is there to really fully determine it. Then there is a transition region where actually this k would be fractions that represent some propensity or some chance to eventually turn out 1, but they are still not determined or not fully determined. And then after, for starting from bit number n plus k, these bits here are totally undetermined. And you can have here an example, let's say with k equal 5. So if now you vote, the majority here over these 5 bits is clearly a 1, so you get a 1 here. Now if you try to already compute the next one, here you have only access to 4 of them. The 5th one you don't know yet, but you already see that whatever the 5th one will be, there will be a majority of 1. So here you get also a 1. Then if you go to the next one, here you have already 2 ones out of the 3, but you don't know the value of the next 2 random bits, but still there is a good chance that the majority will be a 1, and so on. Okay, here comes yet another example of an intuitionistic number, which is a very typical intuitionistic number that already, Brouwer also presented these kind of numbers. The terminology is mine. I call them mortal number. So here the nth element of this choice sequence is 1/2 plus or minus, depending on the value of the nth random bit, 10 minus n. So it's the nth digit here. And clearly you see that if Rn is 0, then alpha n will be larger than 1/2. And in the other case, it will be smaller than 1/2. Now this, I call this a mortal number because this goes on, this definition here, until by chance, the last n/2 random bits all happen to have the same value. Let's say they're all equal to 0 or all equal to 1. And n is large enough and even so that there is that n/2 is well defined. And in this case, when this condition happens, then the series terminates or dies, and it sticks to the value it has at that time. Now, because the probability of termination decreases exponentially, because this n/2, of course, becomes larger, so the probability that all the bits are equal decreases exponentially. Consequently, there is an a priori probability that the sequence goes on forever, so never dies, never stops. And in this case, a proposition like alpha is smaller than 1/2 is neither true nor false, but indeterminate. Of course, once it is the mortal number died, then it either is smaller than 1/2 or larger than 1/2, but as long as it is still alive, ongoing, this proposition is indeterminate. So I'll come back to that, but so here, so this is very important, and I will come back to this example in a few slides. But before, let me present a last example of intuitionistic numbers, which I call an autonomous number. So far, all examples were such that the function that defines these choice sequence elements were dependent explicitly on n. Here it doesn't depend on n. So I just defined that the next element is the previous one, plus or minus some function of n, of alpha n. And you see that this, what I add here, has two fixed points. If alpha n is equal to 1, then it doesn't move any longer, or if alpha n is equal to 0, it doesn't move. So they are fixed points. Moreover, you could easily prove that this alpha n converges actually either to 1 or to 0, and it converges to 1 with the probability of the initial condition, or to 1 with the complementary probability. Now this, here it comes. This example of this autonomous number is actually very similar, for those who know, about stochastic Schrödinger equations that people use in collapse models, in spontaneous collapse and localization models in quantum mechanics, this GRW model or quantum state diffusion model, which I worked 30 years ago, 30 years ago, more or less. So it's the same kind of mathematics, and I find it interesting to notice that some of these intuitionistic numbers have a very similar flavor to the stochastic Schrödinger equations, in which the quantum state eventually collapses to one of the eigenstates of some operators. So here the photon number in the example illustrated here. What is it? Yeah, okay, I have to. So intuitionistic logic. So time is essential. Of course, we don't know in advance the outcome of this true random number generator. And so this kind of proposition, alpha smaller than 1/2, is indeterminate as long as the mortal number didn't die. And this is really very similar to the proposition it will rain in exactly 1 year from now at Piccadilly Circus. Presently, in an indeterministic physics model, this kind of claim or proposition is indeterminate. And you see the similarity with intuitionistic mathematics. So here we see, and that is certainly perturbing to the classical mathematicians, namely the law of the excluded middle is not valid. And consequently, you cannot have any non-constructive proof in intuitionistic mathematics. And it is surprising, though I think it makes plenty of sense in an indeterministic world. The continuum. So the elements of the continuum, these intuitionistic real numbers, are really evolving sequences of computable numbers. And for some sequences, they will never end. So you really have to wait to the end of time, or some people say, until you get a determined value. Okay, I already said that. And one consequence of that is what is called today Brouwer's theorem. This theorem says that all total functions, so a function is total if it is defined everywhere, so all these functions are continuous. So in other words, there are no step functions. And this is really due to the fact that suppose that you would have a step at the value 1/2. But then for this mortal number which I introduced, you wouldn't know, as long as this mortal number didn't die, whether you have to put it on slightly on the left of 1/2 or slightly on the right, before the step or after the step. And so you cannot really define the value of such a mortal number. And because you cannot define it for step functions, it would not be a total function. It wouldn't be defined everywhere. So if it is defined everywhere, it has to be continuous. So this is an example of a theorem which is correct in intuitionistic mathematics, but is not correct in classical mathematics. Of course, you can always simulate a step function with a function that moves very quickly from one level to another. And that's what Brouwer and also Karl Posse name the fact that this intuitionistic continuum is viscous. Somehow you cannot pick out a point from this from the set of these intuitionistic real numbers. Like in honey, you cannot take out just one molecule of honey because it is sticky or viscous. Another consequence is that the intermediate value theorem does not hold in intuitionistic mathematics, although here clearly it is correct in classical mathematics. So this intermediate value theorem tells you that if you have a function, a continuous function that starts, let's say, negative and becomes positive at a larger parameter, then it has to cross zero. Now, it is surprising again that this intermediate value theorem doesn't hold. How can you do without this intermediate value theorem? We use it quite a lot in physics. But you have the following theorem, which is now a theorem in intuitionistic and in classical mathematics, which says the following: if you have a continuous function, so which goes from negative to positive, then for every epsilon, you can construct, that's very important, you must have a finite algorithm, you can construct a value x, which lies between a and b, for which the value of the function is arbitrarily small. So this is good enough for in physics for all practical purposes. Another example is Gisin's theorem, again a theorem very important in physics, or more from quantum physics. And the proof of this theorem, of the original proof by Gisin, does not hold intuitionistically. However, you can change the proof, adapt the proof to intuitionistic mathematics, and this was done, such that you have actually a constructive or intuitionistic proof of Gisin's theorem. So here you don't change the theorem, you change the proof. Arithmetics. Well, obviously you can add elements of choice sequences, or you can apply a computable function to these elements. And you can then look at this relation, this order relation, which is defined in exactly the same way as we are used to, except that here you have to be able to construct these integers k and n that define this condition. However, here, this relation is not a total order, it is only a partial order. As we have already seen, if alpha is my mortal number and beta 1/2, then it could be that alpha is not, you cannot claim that alpha is equal to beta, you cannot claim that it is smaller, you cannot claim that it is larger, because it is not. On the other side, you can introduce a new relation of apartness, denoted like that. Somehow, let's say the intuition here is simply that you can really, alpha and beta are apart if you can put your finger in between, if there's this little region in between. And then according to intuitionism, the negation of alpha is apart from beta implies that alpha is equal to beta, but it doesn't go in the opposite direction, because the negation of alpha equal beta doesn't mean alpha different from beta, it could be just indeterminate. Okay, so I'm coming closer to the end. Yeah, see that's the hour is almost over. So the mathematical language we use when speaking physics has a huge influence on the worldview that physics presents us, as I have already emphasized. And here in this little table, I like to just present some, okay? Okay, to present some correspondence between concepts in indeterministic physics on the left and concepts in intuitionistic mathematics. So in indeterministic physics, past, present, and future are not all given at once. And similarly, digits of real numbers in intuitionistic mathematics are not all given at once. Time passes is represented by numbers, which are processes. In determinism, numbers contain finite information. The present is thick. You know, the present cannot be infinitely small or thin. Resonates with the fact that the continuum in intuitionistic mathematics is viscous. The future is open, no law of the excluded middle, becoming choice sequences, experiencing intuitionism. Now, this really, I like to come back to the initial motivation, and I will then stop here. So here I'm just quoting Sabine Hoffenfelder. Okay, I appreciate her. I like her book, for instance, Lost in Math, which I think is a great book. But in this YouTube presentation, I think she was really taking the view of most high energy physicists. And she was actually very explicit. That's why I like this to present that. So she was saying in this presentation, you are here to hear what science says. Initial conditions determine all events, including chaotic systems. The entire story of the universe was already determined at the Big Bang. We are just watching it playing out. We know, she claims, the future is determined by the present. And she even concludes, if you think otherwise, you are denying scientific evidence. So clearly, Sabine Hossenfelder knows about classical mathematics, no doubt, but doesn't know about intuitionistic mathematics. And that goes on. You can find books where free will, time are all illusions. And the usual picture, and Sabine says that very explicitly, you are watching it playing out. That's like being, a movie. And a movie, everything, of course, all the character, all the story is already on the bobbin. And it's on the bobbin since the beginning. That's the initial conditions. And if you're now watching a movie, you're just watching it playing out. Nevertheless, if you watch a boring movie, time passes very slowly. If it is funny, like apparently here, you may smile and so on. So the spectator certainly experience the passage of time. Time is not in the bobbin, it is in the spectators. But if you now apply this analogy to the physics of the entire universe, in the entire universe, there is no spectator. There is no we that are watching anything. There is just the bobbin. So everything is in the bobbin. That's the initial condition. And that's where one could, my hope is that by moving to these different mathematics, we can gain a different worldview. Okay, so here I think I'm a bit too late to go into all that. So let me just jump to my conclusion. Sorry about that. You have if you want, you have these here. And anyway, the slides are on the server somewhere. Okay, so here my conclusion. Maybe one thing, so I'm not going to repeat what I have already said, just this here. So intuitionism, and that's something again I like, brings classical closer to quantum. You know, all the discussion around quantum physics and all its peculiarities were always addressed by trying to make quantum look more classical, adding supplementary variables and things like that. And I think maybe we will gain a better understanding of quantum physics by bringing classical mechanics closer to quantum. And the other thing I want again to cite Bishop, classical mathematics can be regarded as a branch of constructive mathematics, whereas to regard constructive mathematics as a branch of classical mathematics is impossible. Okay, sorry to be a little bit too long, and I think I'll end here. Thank you very much. And I'm very much looking forward to answer questions.
Thank you, Nicolas. I'm sure there are questions. Peter?
Yes, thank you. Thank you for that talk. I think I understand what you're saying. Don't you run the risk of getting into a kind of a paradox? If you say that there is either an excluded middle or no excluded middle, if you choose the latter, then you might find in the end that there was an excluded middle after all.
I'm not sure I understood what you said. So if I assume there is no excluded middle, I may at the end find out that there is one. Is that the question, or that?
Well, and the excluded middle says that you choose one possibility or another possibility. One or other is true. You're making a statement that you say is true. There is no excluded middle. But once you start saying that, you run into problems.
Well, okay. I don't think that this is true. I mean, there is all these branches of constructive mathematics that exist since more than a century that are have been developed by many mathematicians and philosophers, and they indeed exclude the law of the excluded middle, and they've never faced any contradiction. So I don't expect me to find any contradiction, and neither. I don't see why there should be one. I mean, again, if you just start from the viewpoint that the future is open, then a statement like it will rain in a year time from now at Piccadilly Circus is clearly a proposition which is neither true nor false today. Not only do we not know, that's of course we don't know, but in addition to the fact that we don't know, it is just not yet determined.
Okay, then Enrico Jr.
Yes, hi, hello. Sorry, I was wondering whether if you go to slide 36, where you make this parallelism between the indeterministic physics and intuitionistic mathematics, I was wondering whether it makes sense or should or can be that if there is, you know, the mathematical equivalent of the Planck's constant, because since you know it's so crucial for indeterministic physics, what it corresponds to in the intuitionistic mathematics.
Yeah. Yes. Yes. Yeah, I think it's a good question. So indeed, I started here with this classical mechanics, and I think in classical mechanics, especially of course in chaos, because for integrable systems it doesn't play a role, but for chaotic systems it plays a role. You get this indeterministic view. Now I should also try to apply intuition, not me only. I mean, everybody should try to apply intuitionistic mathematics to quantum physics and to relativity. Actually, I'm not working on applying it to quantum because quantum is somehow already indeterministic. So I'm not sure it needs indeterministic mathematics. However, what I'm certainly trying to do with my co-worker Flavio Del Santo from Vienna is to try to apply these ideas to relativity, because it's actually relativity which is the main argument in favor of determinism. And so that's where I think we should try to apply these new ideas. And that's that's ongoing research. So I cannot really tell you, okay, we have this paper which I just cited very quick at the end, but there are still many open questions here.
I have a question, if I may.
Yes.
Okay, as a physicist, let's say I have some doubts about the statement that real numbers could be thought as hidden variables, quantum mechanics. I mean, in my prejudice, I see the formalism of fluctuations more like Feynman path integrals in quantum field theory. So I understand that you can evolve through many different paths with different probabilities and so on. But, and certainly your discussion about real numbers is extremely interesting, but maybe I'm not familiar with this, but I have some prejudice against the fact that you can make this connection. For instance, I mean, if you have a real number, representation in bits of a finite real number like pi, okay, this bit representation can change if you change the kind of representation. I mean, instead of binary, you use, I don't know, octal or hexadecimal or whatever. So this string of bits will change, even though you will say it's known from the beginning. Okay, and then you also made a very nice example, which I didn't thought about mortal numbers. And mortal numbers are very interesting, but they have a sort of lifetime in the sense that a certain sequence dies, let's say, after a certain time. So it has a finite lifetime. And so the prediction of what happens after depends on how much you.
Maybe I'll, sorry to interrupt, but I mean,
sorry.
I have to remember also all what you asked. So first,
sorry.
real numbers. I'm not claiming that we are hidden variables of quantum, but of classical mechanics.
Okay. Sorry.
It's the analogy of let's say Bohmian positions or other hidden variable models of quantum mechanics, but here it is hidden variables of classical mechanics.
Okay, thanks. Yes.
Yeah, and then you made the correct point that indeed I was using bits or sometimes digits or so on, and indeed of course everything changes if you write the same choice sequence or the same element of the choice sequence in bits or in decimals or any other basis. I should have mentioned that important is you have always a finite information, and it's this finite information that is growing as time passes. It's not necessarily an additional bit. It could be just, if it's in hexadecimal, you would have additional information about these hexadecimals and so on. But it's convenient to represent this additional information in bits, but it's indeed not necessary. You're right. What is important is that the amount of information and which information is available at time step n. What was then your last point? No, sorry.
I don't know if I don't want to become boring, but for instance, the other thing that we said that in a voxel of space, there should be a finite amount of information. Yeah. This is in quantum field theory is a big problem, if I understand correctly nowadays. I mean, in the sense that if you look at all possible states that could be inside this vacuum, quantum vacuum, well, it could be a finite amount of information, but at the state of the art, it's certainly an enormous amount of information. Okay, mm-hmm. Which
okay. I think I understand. Yes, so I didn't really. I'm also not a specialist in quantum field theory and so on, but I think it should be pretty obvious that in physics, everything at least we do in physics, at least in applied physics for sure, deals with finite information, because at the end of the day, everything can be simulated on a finite computer. I think that this example of the climate physics, which is I know very far from quantum field theory, but is an example where although in principle you would have all these initial conditions with all these real numbers, unlimited series of positions of all the molecules, whatever, in practice you never use all that. And so when you tell the story of how the climate evolves, you're telling a story in which you have finite information density.
I see. Yes, that's a good point. Yes, thank you.
Welcome.
Can I ask a question?
Please, let's go, by fairness, along the list here. Otherwise, everything gets messed up. So next one is Jeremy.
Yes, I have a question concerning the free will delusion book that you mentioned. I think you didn't have enough time to go into details, but I wanted to ask if you think that indeterministic physics and mathematics can change anything in how we perceive free will. In other words, if you think that it opens room for free will to exist.
Yeah, so the answer is that randomness or indeterminism by itself is certainly not enough to describe or to understand free will, nor is determinism. So free will requires something in addition to determinism or indeterminism. Okay, then I can tell you more about my view about free will, but I think free will comes first in the logical order. You need free will to have a meaningful conversation as we are having now. But I agree with you if that was the point, that indeterminism by itself will not solve the free will question.
Exactly, that was my concern. Thank you.
Okay, next one is Timo.
Hello, thanks. I had a question in the beginning. you had an example of a couple of integers, and the last one was sort of 0 if the Goldbach conjecture was true, and 1 if it wasn't, or the other way around. And you said that this integer wasn't determined, and I was wondering whether there's sort of some, is it possible for something to be universally determined? Because it seems like if you solve the Goldbach conjecture, then this integer becomes determined for you, but if you don't tell anyone, for example, then it's still undetermined for them. So is there sort of some observer you need to introduce for whom this is determined or not?
Yeah, okay, thank you for this question. No, so for me, no, very important is that it's not a matter of having an agent who becomes conscious of some information. For Brouwer, it was like that. So Brouwer, again, was a kind of solipsist, so it was for him. But then the way, so here it's more a kind of historical presentation, how things started. And indeed, I didn't use this idea of the Goldbach conjecture. I think it's much better because I want to have a kind of objective understanding of indeterminism, which is just a fact of nature. So I assume that nature is able to produce these random numbers and not idealistic idealized mathematician. So indeed here, this is, I should have maybe said that this is really a historical example. Brouwer himself introduced that. But you're right, if you present the thing like that, you end up with wondering, I mean, who should know about the Goldbach conjecture and so on. So this is clearly not the way to use or to define intuitionistic mathematics if you want to use it in physics, in objective physics, where things, including the value of these numbers, of my mortal number, for instance, has some universal value, not a value with respect to some agent.
Okay, thank you very much.
Welcome.
Tom?
So I have a very naive question. I would like to understand whether, because your conclusion was a little bit controversial for me. I mean, one lady is saying something, and probably, hopefully she's not right, maybe she's right, doesn't matter. But is there, from your point of view, or is there a possibility to define a physics experiment such which would clearly say whether your view or her view is okay? So physics experiment. And then another thing is whether you can put a mathematical problem in such way that you can make it, which would lead to distinguish both theories in a real life somehow by any measurement in physics, in life, whatsoever. Am I clear or not, please?
Yeah, I think so. Let me try and you tell me if I understood you correctly. So indeed, so I think, so Sabine says several things. So first she says that one possible view is superdeterminism. And that's okay. That is certainly one possible view. What I'm saying is that this is not the only possible view. You can also use the other view about indeterminism. And indeed, if you use classical mathematics, superdeterminism is a very natural worldview. If you use intuitionistic mathematics, then indeterminism is a very natural worldview. But Sabine says something else. She claims that if you think otherwise, then you are denying scientific evidence. And I think this here at the end, this is wrong. This is clearly wrong. Because indeed, you can just change the mathematics, the language you use, and you come to different conclusions. So I don't think there is just, there's no way just to say that one, so determinism is correct or indeterminism is correct. Both are open possibilities. Maybe there's one thing more I want to add. I was, of course, a bit fast here. Where is it? Ah, yeah, here. If you do a Bell experiment and you assume these two assumptions, which are written here, so no instantaneous communication at a distance, no conspiracy, and then, of course, that is an experimental fact, then you really get by a theorem, a mathematical theorem, the fact that the outcomes of these Bell experiments must be truly random. So how does Sabine answer this? She doesn't deny the theorem. I mean, she's a good person. And what she denies is, okay, she wouldn't, of course, formulate it that way, but what I have here is no superdeterminism. They exist independent variables. And she would say, no, there exist no independent variables. Everything was set at the beginning, at the Big Bang, let's say, in the initial condition. And there is no way for any experimentalist to choose which experiment to perform. You cannot choose, Alice cannot choose which measurement she's performing or how to orient her polarization beam splitter. And okay, of course, if you assume from the beginning superdeterminism, you end up with superdeterminism. If you don't assume that, then with this result here, independent of the mathematical language you use, you end up that the outcomes of some experiments, at least, are truly random.
Yeah, okay, I understand. So maybe here on this page, sorry, correct me if I understood you wrongly, but this is something what you can, with Sabine, dispute. I mean, if she will claim something, you can disprove her. Still, I would like to understand whether it is just about language. I mean, in principle, I will say it like this. Mathematics is just a tool. This is just a language for our real world. And it's extremely perfect that we can use some language to describe the physics, the reality. Yeah, but still, I mean, there must be a connection, or maybe there is a direct connection between mathematics and our real world. Like we do not see complex numbers, but we have them, right? And I would like to see whether there is a way how we can understand which language is actually the correct one, which realization of mathematics is proper for our world. Maybe I'm not clear, but maybe yes.
I think I understand. So I think that the best answer I can give is that if you have the view that the future is open, then the good mathematics is intuitionistic mathematics. If on the other side you are happy with superdeterminism, then classical mathematics is good enough. Remember that classical mathematics is nothing but intuitionistic mathematics seen from the end of time. So you just look at everything from the end of time and think everything, all the randomness you put in the initial condition. God played all the dice at the beginning and coded all the outcomes in the initial condition. If that is certainly a possibility, a logical possibility. Personally, I find it strange, but it is certainly a logical possibility. So I don't think I can see how to argue, I don't see how I can convince Sabine that she's wrong. I can certainly convince Sabine that there are alternatives to what she's saying. So one can support indeterminism without contradicting science. Actually, all quantum physicists do that. But indeed, you could also defend the view of superdeterminism. Einstein was convinced of that, and yeah, what can I say? I'm not contradicting Einstein. I'm not contradicting superdeterminism. I'm just claiming there exist alternatives, and indeterminism is a physical possibility.
Okay, thank you.
Welcome.
Okay, Kenneth.
Hi. It's a while since I've read any of this, but so what I think that you are saying is that we should re-examine a metaphysical interpretation of mathematics. And this is based on intuitionism, but it was my understanding that intuitionism and classical mathematics were equally as provable. If this isn't correct, then it kind of falls. But if that's so, then do you really need to motivate changing our view on indeterminacy in this way? Shouldn't we just say that physics can just have various metaphysical interpretations and mathematics is just another metaphysical interpretation?
Yes, I guess I would agree indeed. I mean, you can have different interpretation for physics and you have these different mathematics. But still, if you take one of these mathematics, let's say classical mathematics, then the view of superdeterminism is the natural view. it's very difficult to add randomness if you know, your mathematics is everything is determined. You have this law of the excluded middle. On the other side, if you have intuitionistic mathematics, then it would be very difficult to defend superdeterminism in physics. So I think they really go, you know, go together, these two. You have the alternative on the physics side, and you have this alternative on the math side, but that doesn't give you full possibility at the end. I think they really come, you know, two with two, they come together.
But doesn't the provability of classical mathematics and intuitionism give you the, you can mix it if you like, because you're going to say the same thing whether you choose intuitionist logic or classical?
Yeah, again, if you do this Belly experiment and you admit that there is a possibility for a physicist to choose which experiment you do, and it's very hard to tell an experimentalist that he cannot decide what he's doing in his lab. But so if you admit that the experimentalist can choose what to do, then according to this theorem, and again, assuming also no instantaneous communication at a distance, then you get, and you have no longer any choice, you get randomness out. So there is here in this example, you have a very strong and I find a compelling argument in favor of indeterminism. But again, I have still to assume, to accept that there are these two assumptions. And of course, someone like Sabine could indeed say, no, there is superdeterminism, there are no independent variables. And this is really her view. I mean, I had exchanges with her. We go on, well, it's not that we have a fight here. But she would indeed publish papers and say, no, this second assumption here, of course, she wouldn't call it conspiracy, but she would call it superdeterminism. But she would say, no, this superdeterminism is there. And consequently, clearly she's a theorist, not an experimentalist. So she would say, experimentalists cannot choose which experiment to perform.
Okay, thank you.
Okay, Rudi.
Yeah, I totally agree with what you say about real numbers. On the other hand, we need the Hilbert space for quantum mechanics. So if you reject classical mathematics and classical real numbers, we have to reject the Hilbert space as well.
Why?
Now, what?
This is not true. You also have Hilbert spaces in intuitionistic mathematics. They will be defined a little bit differently because they don't rest on real numbers, not on classical real numbers, but on intuitionist real numbers. But you also have Hilbert spaces and vector spaces and scalar products and wave functions. All that you would also have in intuitionistic mathematics.
Okay, yeah, thanks. Thank you very much.
Welcome.
Next one is Sotiris.
Hello. I thought you said at the beginning that you can solve problems, physics problems with these mathematics, but I don't think you showed an example. And the question based on this is, since this mathematics exists since Bohr, why have they not been used and been useful and not been known to solve problems?
Yes, good question. Well, so okay, I don't think I said that with intuitionistic mathematics you can solve practical problems, but you can certainly do is answer, for instance, Sabine, and tell that indeterministic worldview is a possibility. So, for instance, even when Einstein is, where is that now? Yeah, here. You know, when Einstein says that if we believe in physics, we know that the distinction between past, present, and future is an illusion. One way of answering Einstein, maybe you don't consider that as a problem, but you may consider that as a tension, let's say, in physics. You can indeed tell Einstein or Sabine, wait, there are different mathematics in which there is a distinction between past, present, and future. So this is what I wanted to say. Now, why is intuitionistic mathematics not better known? That's a good question. I think it has to do initially with the character of Brouwer, who got in fight with everyone, in particular with Hilbert, and also because he was not really considering his mathematics as part of, I don't know, as a tool to describe nature. He was always using this idealized mathematician to produce new information. And clearly, we don't want to base physics on information created by idealized mathematicians. That doesn't make too much sense to me. And I think, indeed, I might be among the first ones. Okay, I don't know all the history, so maybe there was already someone who made some points along that. But the way I'm presenting the entire intuitionistic story, here it is really with this natural random process. So maybe if you want more, yeah, it's this paper here, which is actually supposed to be published in the proceeding of some conferences. But I think this is the first time that intuitionistic mathematics is really presented, let's say, from a physics perspective, and not from some, solipsist or subjectivist viewpoint.
Okay, next one is Andrew.
Hi there. A quick question on slide 15. You say that the finite information density also applies to Newtonian mechanics. Is that necessarily the case if you had, point particles essentially, and so you could fit an infinite number of point particles in a finite space in a classical mechanics model?
Yeah. So I agree that this is an assumption, that the finite volume, finite information, this is an assumption. This is the way I came to intuitionistic physics. And so I find this assumption here very natural. One could, buy this assumption. And if you buy this assumption, then the rest more or less follows. But clearly you can also define intuitionistic mathematics without this assumption. So this is not a necessary assumption, but I think it's a good argument. And again, at least it's my way into this intuitionistic physics. So when I was doing that part of my work, I didn't even know about intuitionistic mathematics. I learned about that from Carl Possi, who told me that my intuition, for instance, this number here, that this was a typical intuitionistic number. So I came to that from this finite information assumption, but I agree with you that that in classical mechanics you don't need to assume that.
And in a sense, in classical mechanics, you could even say that the distance between 2 points contains an infinite amount of information if you're within if you're within the classical mathematics model.
Exactly. So in the classical mathematics model, indeed, the distance between 2 point particles, or just the distance between the center of mass of 2 classical beer balls, contain an infinite amount of information. But according to now this intuitionistic view, these positions, these classical particles don't have a fully determined position yet. And because their position is not fully determined, the distance between 2 of such particles is also not yet fully determined.
Okay, thanks.
Christos?
Hi, can you hear me?
Yes.
Hi. Yeah.
Yeah, okay. Going on slide, for example, 13, I would like to try and understand the way that you are viewing real numbers. And as such, I would like probably to ask you what pi represents in the indeterministic mathematics.
Mm-hmm.
Is it how fast we can just keep on adding digits on this number that defines it, or is it just, for example, if you say that it's half the circumference of a unit radius circle that defines it?
Yeah, thank you for the question. No, pi is a number in intuitionistic mathematics, but it's a computable number. So there's only a finite information in pi. You know, the algorithm, or one possible algorithm to define pi, is written explicitly here. And it's clearly a finite amount of information here. It's a finite algorithm. And with this algorithm, you can compute all the digits of pi. So all the digits of pi exist somehow at once in intuitionistic mathematics. And this is true for all computable numbers. So for computable numbers, you have only a finite information. You see, you go only for finitely many of these random bits here. And that is enough to compute all the digits. Okay, what I also said with pi, and I don't think it's proven for all computable numbers, but I believe it's correct. You can compute not only all the digits, but you can compute digits of pi or bits of pi without the necessity of computing all the previous ones. You can just jump directly to the bit that you want to compute, which clearly illustrates that these bits are already there. They all are already there, since I can access them directly, and I can access them now. I don't need to wait to access them.
Could the same logic apply, for example, if you say that 1.2, just a random real number, does it also contain infinite amount of bits in non-intuitive?
No. So here, this is not really, the distinction between computable number and non-computable number is the same here as in classical mathematics. So a computable number is a number for which you have a finite algorithm that allows you to compute it. And if there is no finite algorithm to compute it, then it's a non-computable number. And then these are the numbers for which classical and intuitionistic mathematics give a very different description.
I see, okay.
So for all the numbers you are used to, the computable numbers, everything that comes out of a computer, for instance, they're of course computable numbers. And for these ones, there is no difference between classical and intuitionistic mathematics.
Okay, Camilo. Camilo, you must unmute yourself.
Okay, sorry. From a non-professional in this thing, a simple question. Whether the universe is deterministic or indeterministic, can I use in both cases the concept of entropy or variational entropy in the same way?
Yes, indeed. I mean, you can do all the physics that we know, you can do in both mathematical languages.
Does them, when you talk about open universe, open future, would the open future, the solutions for this open future be limited by a principle which stays over it, which is the entropic principle, or not? I mean, this openness, is it limited or not?
Okay, I'm not exactly sure I understand the question. I mean, the fact that the future is open, but not everything can happen. Yeah, even if you have randomness, let's say I have my quantum random number generator, so it can only produce either a 0 or 1. It cannot produce 3. It's not the future. Saying that the future is open doesn't mean there is chaos. There are no laws of physics any longer. Of course, there are laws of physics that limit the possibilities. But still, there are cases where more than one possible future exists.
Okay, thanks.
Welcome.
Okay, let me also pose a point. You seem to put mathematics on par with numbers, and in a way, the digits of numbers are acted upon by something like a Turing machine, which processes one and the other, and creating a sort of a time sequence in this way. Mm-hmm. But of course, there are many other objects in mathematics which are not in this are numbers, like, you know, abstract objects like these groups in arbitrary dimensions, or homotopy groups in n-dimensional manifolds where n goes to infinity and so on. And there are even no algorithms to compute them. So there's no sequential approximation possible anyway. Now, that aims, of course, to the viewpoint of Max Tegmark, the mathematical universe, and he posits, in a way, the whole world consists of all mathematical possible structures. And it's up to us to discover them piece by piece, but they're already there from the beginning. So this seems to contradict your point of view that these things are developing over time. So what's your take on Max Tegmark's vision?
Yeah. Okay, so indeed, so my function here is computable numbers. You may say this is just the output of some Turing machine. That's correct. But it's the original point here is that this Turing machine is fed by these random numbers, which are coming out of this natural random process. So you would have to add to this Turing machine some true sources of randomness. And indeed, so you may say everything is already there, all these mathematical structures, as Max is saying. If you accept that this natural random process is also out there, so the process exists, not the outcomes, but the process exists and is part of the mathematical baggage, then I'm happy with what Max is saying. But I'm not sure we would have to ask him whether he would agree that these can be parts of the mathematics. It could be also that he would consider that all the outcomes are already there. And that's where I would disagree. The outcomes are not there before. So the nth outcome is not there before the nth time step. That's where possibly I differ from Tegmark.
Okay, thank you. I think there are no further questions. So let me applaud you in view of the audience.
Thank you very much. Yeah, thank you for organizing that. I think
it was a pleasure.
It was a nice time for me.
Just because many people will ask, the recording will appear in a few days, maybe next week, on the website. Okay, thank you.
Thank you. Bye-bye.
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 Bye.